going.
We group 35 doing problem 8.6, and so we given the beam with two moments force acting on it. So to start off, we find the reaction forces using the free body diagram here, and then we found that the reaction forces are equal to 0 because there's no force acting on it. Then here we section the first section from A to the first moment. So we have x1 going from A equal to 0 and A equal to little a. Using equation 8-4 from the book is a moment equation, and knowing that m1 is equal to 0 because there's no force acting on the beam at the section and there's no moment acting on it as well, so moment equation must be equal to 0. Integrating it to find the slope of this equation, we find that the first derivation is equal to c1, and integrate it again to find the deflection of the beam section. So we have c1, x1, and c2 right here. Knowing that at x1 the deflection must be 0 with the assumption, we find that c2 is equal to 0. Then the second section that we did was between first moment and the second moment. And again, we're doing the moment equation, find that m2 is equal to moment acting on here. So you integrate again to get the slope between the two moments. And now you have variable c3. And then you integrate once more to find the deflection between the two moments. And now you have this c3 and c4. And we set equations as 3 and 4. So at x2 equal to a over 2, you know that the slope is going to be 0 between the two moments. And then you plug in those numbers, 0 and a over 2, and you found that c3 is equal to negative moment a over 2.
Alright, when x is equal to a, or x1 is equal to a and x2 is equal to 0, we know that the deflection, v1 and v2, is going to be the same because they're connected, and the slopes are the same at that point because they're connected. Alright, knowing that the slopes, or knowing that the deflections are the same, we're going to use equations 2 and 4 and set them equal to each other. So we have equation 2 here, and equation 4 here. And then we're going to plug in our known values of c2 and c3. c2 is 0, c3 is negative moment times a over 2. And then from before we have x1 is equal to a and x2 is equal to 0. We're going to plug that in. So we've got c1 times a plus 0 is equal to moment over 2 times 0 minus moment times a over 2 times 0 plus 4, or plus c equals c4 rather. Canceling all the zeros out, we have c1a is equal to c4, and this is going to be our equation number 5. If you'll remember a little bit ago, we said that the slopes will be the same at that point. X is equal to a, x2 equals 0. We're going to use equation 1 and equation 3 and set them equal to each other. We have equation 1 here, c1, and equation 2, moment x2 plus c3. And we said that x2 is equal to 0, so that's going to cancel out and remove this part of the equation. So we have c1 is equal to c3, and that's going to be equal to negative moment times a over 2. Now using c1 in equation 5, which we found a little bit ago, we're going to have c1 times a is equal to c4. We're going to solve for c4, which is going to be negative moment 0 times a squared over 2. That's our c4. Now, to find our slope at a, we're going to use c1 in equation 1. So we have our equation 1 right here with c1 put in, and we're going to solve for our slope. So basically divide by EI. And we get our slope is equal to negative moment times A divided by 2 EI. That's our slope at point A.
Now that we've solved for C3 and C4, we can plug those values into equation 4. And it's, down here is equation 4, and the value for C3 is here, and C4 is here. Knowing that the maximum deflection is going to occur in the middle of the beam, we set x2 equal to a over 2, and plug that value into the equation that we just solved for. Simplifying down, and then simplifying once again, we find that the maximum deflection is going to occur at -5/8 times the moment times a squared over EI.